Hello, and welcome back to Math 3321, Math Concepts 1. We are going to be talking about uh, introducing Chapter 2, Logic and Sets today. So this is Section 2.1, and the topic of this section is reasoning and logic. So through this section, you should be able to understand and explain quantifiers and their effects on statements, different forms of statements, how to determine whether two statements are logically equivalent, how to develop logical arguments, and how to determine whether an argument is valid. All right, so just some baseline definitions. A statement is a sentence that's either true or false, but not both. So things that are not a statement are things like questions, um, things like paradoxes, like the claim that this sentence is false, um, could be a paradox. And so it's neither true nor false. But statements do not have to be true to be logical statements. We could have like the sky is purple. That's a statement, but it's false. So then we have negations, and negations are statements that have the opposite truth value of the given statement. So the negation of a true statement is false, and so if P, our statement, is true, then not P is how we read that, is false. So we have examples here. Negate each of the following statements. So the first statement here is 2 plus 3 equals 5. So that is a sentence, even though it's a number sentence. We can think of it as a statement because it is either true or false. In this case, we know that 2 plus 3 does indeed equal 5. So this is a true statement. So when we negate it, it should be false. Now, one thing to be careful about when we negate statements is that we want to have the complete opposite of the statement that we have claimed here. So we want to cover all the other cases. So 2 plus 3 equals 6 is a false statement, but it's not the negation of 2 plus 3 equals 5. So the negation of this statement would actually be to say instead that 2 plus 3 does not equal 5. So it equals anything else except for 5. And then a hexagon has 6 sides. Again, the negation of this statement would not be a hexagon has 7 sides or a hexagon has 0 sides. But a hexagon does not have 6 sides is how we would negate that statement. So then some more definitions here. We have statements that might include quantifiers. So quantifiers are words like all, some, every, there exists, and no or none. So these are things that add quantity or tell you about how many of something the statement is applying to. Now we have two different types of quantifiers. There are universal quantifiers and existential quantifiers. Universal quantifiers apply universally, right, to every element of a set. So universal quantifiers are things like all, every, or no, meaning that across all of these things, or every one of these things, or none of these things, the statement is being applied. Now, existential quantifiers refer to the existence of something. So this applies to one or more element in a set. So some or there exists, or for some are existential quantifiers. When we want to negate existential or universal quantifiers, we have to think about what it means to have the opposite of something. So all students like hamburgers. So the opposite or the negation of all students like hamburgers. Take a moment, maybe pause the video, think about what the negation of that statement might be. Would the negation of the statement be no students like hamburgers? I mean, if all students like hamburgers was true, then no students like hamburgers would be false. But actually, no, the negation of all is not none. So the negation of all students liking hamburgers would mean that not all students like hamburgers. So, an intermediate step you might take here is to say not all students like hamburgers. You could also say one student does not like hamburgers. That would be a way to phrase this. So there exists a student who does not like hamburgers. Or you could just simply say some students do not like hamburgers. So that's probably the simplest way for us to negate that statement, to say some students do not like hamburgers. So if we move on to this next example, some people like mathematics. If we want to negate some people like mathematics, it would be that there are no people who like mathematics, would be the opposite of this. Some people like mathematics would be a subset of the claim, all people like mathematics. So all people liking mathematics is not the negation of this statement. But to say some people like mathematics, that's the same thing as saying there exist people who like mathematics. That's the same thing. So to negate that, we could take and say there do not exist people who like math. So to simplify that, we would say no people like math. So negation of some people like mathematics is no people like mathematics. All right, so if we move to a mathematical statement here, this claim says there exists a natural number n such that 3n equals 6. So if we want to make the negation of that claim, there exists a natural number n such that 3n equals 6. There exists is going to have to be negated to say a universal quantifier. So there exists is an existential quantifier, and the negation of an existential quantifier is a universal quantifier. So this would be a for all or for none claim now. So we want to say if there exists a natural number n such that 3n equals 6, the opposite of that would be there are no natural numbers n such that 3n equals 6. Or similarly, we could just claim that for all natural numbers n, 3n is not equal to 6. And this is equivalent to saying there are no natural numbers n such that 3n equals 6. That's the same thing as for all natural numbers n, 3n does not equal 6. All right, and then for all natural numbers n, 3n is equals 3n. So this is a true claim, but we want to negate it. So for all natural numbers n, for all is a universal quantifier. So our negation is going to be an existential claim. So for all natural numbers n, 3n equals 3n. The negation of that is going to be that there is some natural number that breaks this equality. So there exists a natural number n such that 3n doesn't equal 3n. So we can use truth tables to think about if statements are going to be equivalent or not and to find their negation. So a truth table essentially takes a statement, and any statement has to be either true or false. So there's a case where that statement is true, and then there's a case where that statement could be false. And then the truth table, if we wanted to have a column that told us about the negation of that claim, we could say, okay, well, in the case that statement P is true, its negation would be false. In the case that statement P is false, the negation would be true. So we can use truth tables to understand different types of statements. So there's a conjunction statement. A conjunction statement is a compound statement created from giving from two given statements and the connective and. So we use this symbol that's like an upside down V to represent and. I always remember it because if I were to write the letter A for and, I would start with that kind of symbol. And then if I wrote and, I would make the bar across. But that upside down V represents and. So a conjunction is true only if both statements are true, otherwise it's false. So when we have statement P, we know that statement P can either be true or it can be false. So statement P can be true and Q could be true also. Statement true could be true and Q could be false. Then we have if statement P is false, then Q can be true or Q could be false. So these are all four of the cases we have to think about the situations we could have for P and Q. So you could think about statements that apply to your everyday life, like P could be the parking garage is full, and Q could be it's raining. So P being true would say the parking garage is actually going to be full, and Q would be it's raining. So P and Q would tell us the parking garage is full and it is raining. So when P is Q and true is full, then that conjunction P and Q is also going to be true. Now, if P is true and Q is false, then P and Q will have to be false. So if the parking garage is full, but it's not raining, then the parking garage is full and it's raining would be false because one of the two has failed. And in the same way, if P is false and Q is true, P and Q would have to be false because that would be like saying the parking garage is full and it's raining, but the parking garage isn't full. So the conjunction claim would be false. And then lastly, if both statements are false, then the conjunction statement is also false. So if the parking garage isn't full and it's not raining, the claim the parking garage is full and it is raining would be false. And so here's that typed out for you in a slide. We also have what's called the disjunction. So the disjunction is a compound statement when we take two given statements and we connect it using the word or. So this upside or the correct orientation of V gives us the symbol to represent the disjunction or. So disjunction is false if both statements are false and true in other cases. So it's if we have, again, we have these situations, P could be true and Q could be false. P could be true. Oh, I meant to write true. They could both be true. We could have P true, Q false. We could have P false, Q true, or P false and Q false. So P or Q is true, is only false if both statements are false. So in our same example, parking garage is full, it's raining. Parking garage is full or it's raining is true when either the parking garage is full or it's raining, but not true if the parking garage is not full and it's not raining. So P or Q, when they're both true, will be true. P or Q will be true when P is true and Q is false, because P is true. So the or statement's true. It's also true when Q is true, but P is false, because P or Q is true. And it's false in the case that they are both false. We have that typed out here. Okay, so if we want to classify these statements as true or false, we know 2 plus 3 plus 5 is true. 2 times 3 equals 6 is also true. 5 plus 3 is 9 is false, because 5 plus 3 is not equal to 9. It is equal to 8. So if we think about the statement P and Q, P is true and Q is true. So P and Q will be true. Q is true again, R is false. So Q or R is still true, because this statement would read 2 times 3 equals 6, or 5 plus 3 equals 9. Yes, that's true, because Q was true. The first part of the statement was true. And then not P or Q is how we would read the C example. So not P is the negation of our statement P. So not P would be 2 plus 3 does not equal 5, which is false. So this is false. The negation of P is false, or R is false. That's going to be false because both of the component parts of the disjunction were false. Oh no, my symbols are messed up here. But you can try this on your own. We could make this up and figure it out. So let's say that this is a conjunction. Then not P is false, right? Because P is true, Q is true, R is false. So not P is false, and not Q is also false. So false and false is false. So P is false, Q is false, so P and Q, or not P and not Q is false. So let's say that this is an and statement as well. So P and Q will be true because P is true and Q is true. So P and Q is true. So not P and Q is false. So if I make that into an and, then that should be true. All right, and then lastly, let's say P and Q or not R. Let's say that that's the statement here. So P and Q together is true, as we just said, because P and Q are both true. Not R is going to be true because R is false. So not R is true. So P and Q is true. Not R is true. So P and Q or not R is going to be true as well. All right, so then we have a third type of statement. We have, again, conjunction, disjunction, and now we're going to talk about conditionals or biconditionals and biconditionals. So conditionals are what we call implication statements, and they're expressed as if P, then Q. So we represent this with an arrow. We can think about the truth table of this. So again, we have cases where P and Q are both true. P is true, but Q is false. P is false, Q true, and then both false. So If P is true, then Q is true. So let's go back to that example we were thinking about with if the parking garage is full, then it's raining. If the parking garage is full and it's raining, then if the parking garage is full, then it's raining will be true. Now, if the parking garage is full and it's not raining, then the claim that if the parking garage is full, then it is raining, this will have to be false. Now, here's where it gets a little bit tricky. So if P, that hypothesis, the if part of the conditional, is false, then we actually can't say that the implication statement is false because we don't know what would actually happen. So if the parking garage is full, then it's raining. If it's raining, but the parking garage isn't full, we don't really know what would be happening if the parking garage was full. So this is actually true. And both of these are true by what we call vacuous truth. So maybe a better example for this is something like, my uncle said, if I make an A in the course, then he'll give me $10. So we can determine if the uncle is telling the truth, if this implication statement is true, then we can think about what happens if I make an A and if he gives me $10. So if I make an A and he gives me $10, then the implication is true. He was telling the truth. But if I make an A and he doesn't give me $10 in the second line, then he was lying. That implication statement was false. But in the case that I don't make an A, if the uncle gives me $10, then his statement, he might still be holding to his word that if I made an A, he would give me $10. And similarly, if I don't make an A and he doesn't give me $10, he still might be true to his word. He might have been true to his word otherwise. So that's vacuously true, is what we say. And then some more vocabulary. The hypothesis is the first part of that implication, and the conclusion is the second. All right, so we have related implication statements. So if we start with the statement, if P, then Q, then we have the converse, the inverse, and the contrapositive. So I always remember these by using my hands. So if I say the statement is if P, then Q. Then the converse, I'm going to switch the order of my hands. It's going to be if Q, then P. The inverse, if I start back with my statement, if P, then Q. The inverse, I'm going to take my thumbs and I'm going to point into me, and I'm going to negate both of the things. So in that case, I've negated both P and Q. And then finally, contrapositive, like converse, I'm going to switch my order, and then positive, I'm going to change the truth value of both. So I'm going to change the order and the truth value. So the contrapositive of if P, then Q is if not Q, then not P. Okay, so if we want to write the inverse or the converse, inverse, and contrapositive for the statement, if I'm in San Francisco, then I'm in California. So the converse is where we are going to change the order between these two. So the converse is if I'm in California, then I am in San Francisco. Now that's not necessarily true, but it is the converse of that statement we were given. Now the inverse is we're going to keep the same order, but negate both of the component statements. So if I am in San Francisco will be negated to if I am not in San Francisco. And if then I'm in California is if then I am not in California. So if I'm not in San Francisco, then I'm not in California. Then finally, the contrapositive is where we both change the order and the truth value of both statements. So if I'm not in California, then I am not in San Francisco. Okay, so what this example is asking us to do is to use truth tables to prove P implies Q is what we call logically equivalent to not P implies not Q. And this is the statement, and this is the contrapositive. So here we're proving that a statement is equivalent logically to its contrapositive. So we can use a truth table to do this. And just like in all of our other truth tables so far, we have these situations for P and Q we can start with. So all 4 of the situations we will cover. So to show that something is logically equivalent to another statement, we need for their truth values to be the same in every situation. So what we need is for this column here, this column here to match this column here. That's what we're looking for. So we just need to fill out our truth table. So P implies Q. We know that it is going to be true if P is true and Q is true. If P is true and Q is false, then that implication is false. And then the last 2 are vacuously true because we don't really know what's happening if that case is false. So in the example we were just given about San Francisco and California, if you're not in San Francisco, then you could be in California or you could be somewhere else. So that statement, if I'm in San Francisco, then I'm in California. If we don't know what we're talking about where we are, we just know we're not in San Francisco, then we could be in California or not. So that's the vacuous truth. All right, so then we need to negate not Q. So now I'm just going to look to my Q column and say, all right, well, when Q is true, then not Q is false. When Q is false, then not Q is true. When Q is true, not Q is false. And when Q is false, not Q is true. So I'm just doing the opposite of my Q column. And then not P, I'm going to do the same thing. So in the first 2 rows, P is false, so not P is going to be, or sorry, P is true, so not P is going to be false. And P is false in the last 2, so the negation of that will be true. And now I just need to do the implication not Q and implies not P. So here I'm looking at these 2 columns. So when not Q is false, we're again going to have that vacuous truth. And then if not Q is true and not P is false, then that implication is false. And in the case that they're both true, then the implication is true. So I can look at those 2 columns now and see, all right, true, true, false, false, true, true, false, or true, true. So these are logically equivalent, and I've just proved it. So P implies Q is equivalent to its contrapositive, not Q implies not P. All right, and then the conjunction of a statement and its converse is what we call a biconditional. So this would be P, if P then Q, and if Q then P. So I think I'm missing a quotation mark there. Sorry, parentheses. All right, so we can fill out the truth table for the biconditional statement to figure out when this is true. So this is the same thing as P, if and only if Q. So if I start my truth table with all the possible combinations of P and Q, and then my implication statements. So again, true, false, true, true, because of the vacuous truth. And then I go the opposite way. So this is still true. So Q implies P. This is vacuously true. vacuously true because I'm looking at this direction, and then this is false. And then finally, I have the conjunction of this column and this column. So true and true would give me true, false and true is false, true and false is false, and true and true is true. So P, if and only if Q, is true only when both are true or both were false. So here's that typed out for you. All right, and then lastly, we have we can talk about what it means to have valid reasoning. So valid reasoning is if the conclusion follows unavoidably from a true hypothesis. So here's an example. If our hypotheses are all cats like fish, and Felix is a cat, then our conclusion has to be that Felix likes fish. So we can use what's called an Euler diagram, which is kind of similar to a Venn diagram, but it's with logical statements. We can represent the validity of this reasoning. So what an Euler diagram would look like here is that we would take this outer circle to represent all of the things that would fit into the statement, they like fish. So something likes fish. And then cats are a subset of all of the things that like fish based on that hypothesis, because we said all cats like fish. So anything in the circle of cats would have to be in the circle of likes fish. And Felix, he's a cat, so he has to belong to that circle of cats. So since Felix is a cat and he has to be in this circle, and the circle of all the cats has to be contained in the circle of likes fish, Felix is automatically in that circle of liking fish. So here's a little more complicated one. If we want to figure out if this argument is valid. So in Washington, D.C., all lobbyists have influence. Our second hypothesis is that no one in Washington, D.C. over 6 foot tall has influence. And then so our conclusion, we're trying to figure out if this is a valid logical conclusion or not. Persons over 6 feet tall are not lobbyists in Washington, D.C. So we can try to make an Euler diagram to represent this. So if I start my Euler diagram, again, I want to talk about the lobbyists, the people who have influence, and the people over 6 feet tall. Those are kind of my sets. So if I think about the people in Washington, D.C. who have influence, so these are the people who have influence. And I know that all lobbyists have influence. Then I can take my red marker here and I say, okay, these are the lobbyists. So all lobbyists have influence. So I'll just go ahead and write this out. It's people who have influence. So this would be our Euler diagram for that first part of our claim. In Washington, D.C., all lobbyists have influence. So we could also say in Washington, D.C., people in Washington, D.C. who have influence. And now, so our second statement, no one in Washington, D.C. over 6 foot tall has influence. So when I think about the set of people who are 6 feet tall or taller, they cannot be overlapping with the people who have influence in any way, because none of those people have influence. So these have to be the people over 6 foot tall. So my conclusion was persons over 6 feet tall are not lobbyists in Washington, D.C. So we're asking ourselves, would it be possible for these two circles to overlap? And the answer is no, because if the circle of people over 6 foot had to overlap with lobbyists, then it would have to overlap with the people who have influence, and that would contradict our claim that no one over 6 foot tall has influence. So our diagrams could look something like that. And we would say, yes, our conclusion was true. All right, so that is the end of section 2.1. You should be ready to do that 6.1 homework assignment on MyLab Math now, and I hope you have a great day. Thanks.